All right. I was gonna say we should start off with some more implicit differentiation and maybe some more related rates. So let's look at the following. Let's say we want to find the equation of the line tangent to 6x squared plus y squared equal to 42 at the point -1 comma 6. I'm going to say this every time because I just can't help myself. When we're trying to find the equation of a line, we need two things. We need a point and a slope. We have the point already. To find the slope, we take the derivative. I will point out here, if you really, really wanted to, you could actually solve for y. You could do it. So actually, let's go ahead and do that just to kind of show you how it's not the way to do this. So here's kind of the wrong way to do this, just because, but still not incorrect, just not the easiest way. So you could actually say solve for y. Again, we're going to do it the right way in a second, but I want you to just see that sometimes it is possible to solve for y. But now here's the thing. When I solve for y here, y is going to be plus or minus the square root of 42 minus 6x squared. And so if I take the derivative, well, in fact, this isn't a function anymore. It's like the top half of an oval and the bottom half of an oval. And so if I take the derivative, or if I rewrite this as y equal to plus or minus 42 minus 6x squared to the 1/2 power, the derivative here is going to be plus or minus 1/2 times 42 minus 6x squared to the -1/2 times the derivative of the inside, which is -12x. Here's the problem, or here's what's challenging. It's not really a problem. Here's what's challenging about doing it this way. If you're trying to figure out what the slope is actually equal to, and I plug in x equal to -1, so if I plug in x equal to -1, I end up getting y prime equal to plus or minus 1/2 times 42 minus 6 to the -1/2 times -12 times -1 is positive 12. Just to simplify this a little bit here, 12 over 2 is 6. 42 minus 6 is 36. The square root of 36 is 6, but it's a reciprocal. So this actually ends up being plus or minus 6 times 1 over the square root of 36, which is plus or minus 1. But which one is it? Is the slope positive 1 or is the slope -1? It's really, really hard to tell when you have something that's not actually a function of x. Now, we could use logic here and say, well, I know the point's -1, 6, so it's the top half of the oval instead of being, right, because y is positive instead of negative. And so it should be the plus part here. So the slope should actually end up being positive 6. But that's way too much thinking. It's much, much easier to be like, I'm just going to do implicit differentiation. Don't do that. Do implicit, take the derivative, 2y times y prime. Oh, sorry, I was looking at this equation here. Let's, yeah, sure. Plus 12x. I know it's written out of order. Don't hate me for that. Equals 0. And then plug in, right? When you're finding the slope of the tangent line using implicit, immediately after differentiating both sides, that is your moment to plug in your point, to make life easier. So now I'm going to plug in y equal to positive 6 and x equal to -1. So 2 times 6 times y prime plus 12 times -1 equals 0. And then solving for y prime, I have 12y prime equal to positive 12. Y prime equals positive 1. Like we said, it should have been here after we did a lot too much thinking. So this is definitely the way to go. And then we write the equation of the line. This is the calculus part, right? Like the calculus part is finding the slope. The equation is just remembering how to write the equation of the line. Y minus the y coordinate equals the slope times x minus the x coordinate. I would probably encourage you to simplify this. I would write this as y equals x plus 1 times 1 plus 6, or y equals x plus 7. Most of you are in tabs class, but you're not using web work this quarter, but you might use web work next quarter or the quarter after. Something I just want to point out is that web work, in case you haven't used it before, will accept pretty much any sort of unsimplified answer. And I've seen students spend a lot of time typing in a lot of garbage when they could have done some relatively easy simplification on their own. And been like, I've seen people type in like 6 times 1 squared plus 7 minus 5, when you could just like, okay, you can do that math on a calculator in your head and type in like 3 or whatever that number is actually equal to. So it's nice to use the fact that that thing doesn't make you simplify, but it's also sometimes easier just to do the simplification instead of typing in a bunch of garbage. So if you have to use web work in the future, I would say take that lesson to heart. I know it's kind of hard to see that right now, but it's good to simplify stuff to some degree so you can kind of have an idea of what's going on. Let's look at one more implicit example, and then we'll move along here. Sure. Yeah, let's do this one. So let's find dy dx for the equation. Sure. Cotangent of 6x plus 5y cubed equal to x minus 2y plus 3. This one is not the convenient case like before where we get to plug in the point after we differentiate both sides. They're not asking us to find the slope of a line, of a tangent line. They're asking us to find the derivative here. So here we really have to do kind of all the algebra. Cotangent, derivative of cotangent. I should give you guys a quiz, not like for real, but like a trig derivative quiz. You all like, because definitely at this point, the expectation is that you have memorized the trig derivatives. So if you haven't, spend some time this weekend. There's 6 of them. Make a flashcard, make the lock screen on your phone, but make sure you just keep seeing them. If you see them enough, you will memorize them, but you have to actually try to do it. So in fact, since we're here, let's write them all down. Derivative of sine. This pen's starting to go. Is cosine. Yeah, the pen's really starting to go. Okay, you're dead to me now. Derivative of cosine is negative sine of x. Derivative of tangent of x is secant squared of x, and then cotangent goes right along with that. The derivative of cotangent of x is, you should already be saying it in your head, negative cosecant squared of x. Derivative of secant of x is secant of x times tangent of x. And the derivative of cosecant of x better be negative. It's negative cosecant of x times cotangent of x. Get those down. Got to memorize them. Unless your teacher says you don't, I guess. Like if he's giving them to you in some way, I guess you don't have to memorize them, but you should memorize them anyway, even if you should memorize them, because they're not going away. They're going to be around in 16b and 16c. So yeah. All right. So let's find the derivative here of both sides. So the derivative cotangent of some stuff is going to be negative cosecant squared of that stuff. And then we have to multiply by the derivative of the inside here. And we do have to have a parentheses. It's going to be 6 plus the derivative of 5y cubed is going to be 15y squared times dy dx, or I prefer to write y prime. Right? Whenever it's implicit, we're implicitly assuming that y is a function of x unless they say something else. And so every time you take the derivative of 5y cubed, you're getting 15 times your stuff squared times the derivative of your stuff. Equal to the derivative of x is 1 minus the derivative of 2y is 2 times y prime plus the derivative of 3 is 0. You don't need to write the plus 0, but I did. So there you go. Most of the time at this step, you can then like identify where your y primes are, bring them all to one side, bring everything else to the other side. Before we can do that here, we have to distribute this negative cosecant squared of 6x plus 5y cubed. We have to distribute that to the 6 and to the 15y squared times y prime. Hello, good morning. Which is a little bit annoying, but oh well. So we've got negative 6 times cosecant squared of 6x plus 5y cubed. And then I would say plus, but really it's gonna be minus because it's a minus cosecant squared of that stuff times all that. So it's a minus 15y squared times y prime times cosecant squared of 6x plus 5y cubed. Good God. Equal to 1 minus 2y prime. And now we can identify where our y primes are. This term has a y prime, and this term has a y prime. So bring those things to the same side, everything else to the other side. I would bring them usually to the left, although it doesn't really matter which side you pick as long as you are consistent. Not even consistent, as long as you're just doing the work right. You can pick left one time, right one time. You go back and forth every time. Just make sure you get all of them. So let's do two things at once. I'm going to add 2y prime. I'm going to bring that over there. And then from the two things in red, the positive 2y prime and the minus 15y squared, cosecant squared, or whatever, I'm going to factor out the y prime as well, so I don't have to write it twice. I'm going to factor out the y prime. I've got my y prime times positive 2 on the left, and my y prime times all of this garbage here. So minus 15y squared cosecant squared of 6x plus 5y cubed. God, that's terrible. Equal to, add that over to the other side. We get positive 6 cosecant squared of 6x plus 5y cubed plus 1. And then the final step, whenever you're doing this kind of implicit differentiation question, is to divide both sides by whatever is multiplying by y prime here. So y prime equals 6 cosecant squared of 6x plus 5y cubed plus 1 over all of that. 2 minus 15 times y squared times cosecant squared of 6x plus 5y cubed. Ugh. No, nothing cancels. This is as simple as it gets. Those cosecant squareds, we cannot cancel them, unfortunately. Not unfortunately, I mean, because of math, right? We can't cancel them because that's how the math works. Not really, unfortunately. Questions about any of what happened here? Peyton and Eric, I was just reminding everybody that we should definitely have memorized the trig derivatives by now. So if you haven't, this is a good weekend to do that. It's a good weekend to make the lock screen on your phone or make some flashcards. Think about them when you're in the shower, when you're taking a bath, when you're walking to school. What's the derivative of cosecant? Oh, it's negative cosecant times cotangent, right? That's what I mean. That's what's going on in my head sometimes. I'm like, I mean, not the derivatives because I know them, but like there are math problems. I'm like, oh, that's interesting. That's just on my way to work, whatever. That's the brain of someone who knows they need to learn some math, is they're thinking about the math. All right. Let's do some related rates. Related rates are interesting problems because usually I would say a related rates problem, in addition to being a mathematical problem, is also a reading comprehension problem. I will also point out, how many of you have to take stats eventually? Probably many of you. Stats really, okay, there's math there, but really much of your statistics success is based on your ability to read and interpret things correctly. So it's really about reading comprehension and also using that mathematically. So it's good to practice our ability to read and interpret things in the right way. Let's look at some examples here. Sure. Yeah, let's look at this one. So we have, sure, it's been science. I'm like, okay, yeah. A balloon is being blown up with air at a rate of 15 cubic centimeters per second. How fast is the radius of the, I'm not going to write, but the spherical balloon, right? We're going to assume this balloon is a sphere shape. How fast is the radius of the balloon increasing when the diameter is 22 centimeters? And for one like this, I don't really think we need to draw a picture, but I'm gonna draw it anyway. There's my balloon. There's my radius. My radius is getting bigger, right? The balloon is getting blown up. Okay, so first step, and I want you all to try to do this on your own without me for a second. I want you to identify what I really say what we care about is changing, right? Not just what is changing, because technically you'd say the radius is changing, the diameter is changing, the surface area is changing, the volume is changing, but what are the things that are changing that we care about? Which is too much to write. That's why we just say what is changing. All right, so you all should be, there should be two things in this list here. Thing one and thing two. And then you should write a derivative. D something dt should equal something. And d something dt should be something we're looking for. There's one rate of change we know. There's one rate of change we're trying to find. Know this one. We want to know this one. What's the word I'm looking for? So let me ask you all, in the words I've written here, what is the quality? What is the thing about the balloon that we know how it's changing? Is it the radius? Is it the surface area? Is it the volume? Is it the perimeter? What is it? They told us how the what was changing. Did they tell us? They didn't use the words that I'm asking you to find, but that's where you want to use some dimensional analysis. So they told us that something is changing or blowing up the balloon at a rate of 15 cubic centimeters per second, which means we are definitely talking about volume, right? Because volume is some unit length cubed. If it was square centimeters per second, we'd be talking about area. If it was centimeters per second, we'd be talking about length or radius. So basically, when they tell you something, they should be giving you the right units. You basically just look at that number. If it's a 3, you're talking volume. If it's a 2, you're talking area. If it's a 1, you're talking length. So we know that volume is changing in some way. And we're going to write dv dt is equal to the rate of change that was given. 15. I don't really want to write the units on there, but you can. Cubic centimeters per second. Great. And then they're asking us how the radius of the balloon is changing. So we want to know how the radius is changing. So we're trying to find dr dt. After you've identified the thing that you know how it's changing, the thing that you want to know how it's changing, our typical job is to find an equation relating those two things. Sometimes there'll be extra things in your equation. Specifically, if you're talking about cones, cones are always a pain in the butt. There's always like an extra thing in there that you have to deal with, but that's life. So here, there's a nice equation relating the volume and the radius of a sphere. The equation is volume equals 4/3 times pi r cubed. Maybe after this, we'll take a moment to talk about the area and volume equations you should be aware of for cones and for the shapes in the section, because there are a few equations you should be aware of here. Let's see here. So what do we do next? Yeah, or more generally just differentiate both sides. But yeah, and we are going to use implicit here because we're going to differentiate both sides with respect to time. So we're imagining volume as a function of time and radius as a function of time, and we're going to differentiate. When you see these letters WRT, that means with respect to time. People use that abbreviation a lot because it comes up a lot. So we differentiate both sides. The derivative volume isn't 1, it's v prime of t, or dv dt. So we're going to get dv dt equal to 4/3 times pi times the derivative of r cubed is going to be 3 times r squared times the derivative of r. It's just the chain rule, right? Implicit differentiation is really just the chain rule again, where the stuff is r, right? The derivative of some stuff cubed is 3 times your stuff squared times the derivative of your stuff. We've done all the calculus. The rest of this is plugging in the things you know, solving for the things you don't. Did I give you? Yeah, we have enough information. Okay, cool. So I know I'm trying to find drdt because that's what the question asked. The thing you're trying to find should be the only thing you can't plug in for. Everything else we should have a value for. So plugging in, we're given that dVdt is 15 centimeters cubed per second. I'm going to cancel those threes there and get 4 times pi times, they also gave us the radius. Kind of. Don't get fooled, right? I mean, it's not, it'd be easy to, it'd be not that hard. I don't know. I'm trying to say words like, this isn't, I shouldn't make the mistake of saying the radius is 22 because they told us the diameter was 22, which means the radius is 11 squared times drdt. I don't usually write units in here because I'm just going to write the units at the end, but we will go back and talk about that in a second. So then I'm just going to not multiply this out because I don't want to. I'm going to say that drdt is equal to 15 divided by 4 times pi times 11. Okay, we can multiply it out. 11 squared is 121. 4 times 121 is 484, right? There's no carrying. Right, multiplying by 121 by 4 is not that hard because there isn't any carrying that happens. 4 times 1 is 4. 4 times 2 is 8. 4 times 1 is 4. It's 484. So 484 pi. What should my units be if I'm asking how a radius is increasing? Should it be centimeters per second, centimeters squared per second, or centimeters cubed per second? Are we talking about a length, an area, or a volume? If you're talking about the radius, a length. So it should be centimeters per second. Now, if you're not sure, you can look back and say, well, the units on 15 here were centimeters cubed per second. And the units on this 11 were really 11 centimeters. So really, I have centimeters cubed per second divided by centimeters squared. Centimeters cubed divided by centimeters squared leaves me with 1 centimeters, and there's still a per second left over. So the units do match up. And they always should match up. They should always come out to be the right kind of thing you're looking for. Any questions about any of this? Yeah. Yes, I would leave the answer as 15 over 484 pi centimeters per second. Yes, I would. And so if I was trying not to write any words, I would leave it like this. But I might also write the words like literally the radius is increasing at this number, centimeters per second. There's something else I want to say here. I would point out, in my mind, this is the usual 4 or 5 step process. Draw a picture if it makes sense. Figure out what's changing. There should be at least 2 derivatives you have to deal with. The thing you're given and the thing you want to find. Find an equation relating those variables. That's called related rates. We're relating those variables. Differentiate both sides, plug in and solve. Those are our 4 steps for this process. Or 5 if you're drawing a picture first. Let's talk about things we should know the volumes, areas, whatever's of. So there's a few shapes just to be aware of that come up in these kinds of problems. Let's talk the words. Let's start with the 2-dimensional shapes first. So 2-dimensional shapes that we should know formulas for, or that we should be able to look up or somehow find out. So squares and rectangles, I don't think are that big a deal, right? Square, rectangle, they're kind of the same, but you might label them differently. So the square, all the sides are the same length, and you can call them all whatever letter you like. I would typically pick X. The area of a square is X squared, which is, I think, the reason why we call that exponent being not, we don't say X to the 2, we say X squared because of this equation. That's how you get the area of a square. Just like when you do X cubed, the volume of a cube is X times X times X, X to the 3rd. The perimeter here is X plus X plus X plus X. For a rectangle, it's a little bit different. The area is X times Y. The perimeter is 2X plus 2Y. Let's see, what other shapes do we need to talk about? Triangle. Typically, the only thing anyone's ever going to really ask you about a triangle is the area. So the area of a triangle is just 1/2 base times height. They could ask you about the perimeter. The perimeter is just add up all the sides, but I almost never see perimeter questions about triangles, so I'm not going to really worry about it. There's not like a nice formula for the perimeter of a triangle. It's just like add up all the side lengths. What other shapes are important here in 2 dimensions? A circle. So circle, we have the radius there, and I would say that the area of a circle is pi times the radius squared. The circumference of the circle is 2 times pi times r. And I guess you might need to know that the diameter is equal to 2 times r. Although that's, I feel like, not really right. Any other shapes? Any other 2-dimensional shape? We'll get to 3-dimensional shapes in a second for sure. One other shape that could come up on occasion is, and actually will come up in 16B in another way, so we might as well mention it, trapezoid. So trapezoid, I always think of a trapezoid as having 2 parallel sides and 2 non-parallel sides. There are lots of different ways, right? These 2 non-parallel sides can be kind of oriented any which way. They could be very close to being parallel, or they could be kind of anti-parallel, or one straight, like there's lots of options here. If we call this the height and this the base 1 and this base 2, then the area of the trapezoid is equal to, I always like to think of it as the height times the average of the bases. Because really you could think of literally taking this little section here, cutting it in half, and taking this little triangle here and flipping it around to go right there. So now you've got a rectangle whose height is still h and whose base is the average of those 2 bases. Kind of neat. So those are the things you know. I mean, I feel like trapezoid probably don't really need to know, but the circle definitely you need to know. The square and the rectangle, I think, are not too terrible. Let's talk about the 3D shapes because I feel like those are a little bit more complicated. Let's see. So 3-dimensional shapes. Or I guess I should say solids. I don't know, whatever. And we'll kind of go in the same order of types of shapes. So let's talk about a cube. So when you're drawing a shape, it is kind of up to you to label the sides how you want to label them. I typically default to using X's and Y's because that's what most math people use, but that doesn't mean you have to use those. You could use length, width, and height. You can use whatever. But the one thing I will say is you should never use more variables than you need to. Meaning in this cube, I shouldn't label the sides X, Y, and Z because they're not all different lengths. We know that in the cube, all the sides have the same length, so we should give them all the same name. If things are always the same, we should call them the same thing. So then the volume here is 6. That's not the volume. That's the surface area. The surface area here, sorry, is one face is x squared, and there's 6 of them, so it's 6 times x squared. I know, I'm sorry. And the volume is x times x times x, which is x cubed. There is no length to speak of here, right? We wouldn't say this thing, right? It has a surface area, it has a volume, but the length would be a weird thing to try to even talk about. And then we have a 3D rectangle, or more officially called a parallel piped, which is a terrible word to say and write. Really just a rectangular box. So that looks something like, something like that. You could draw on the other sides if you want. So here's where we have to give things different names. So like this side is X, this side is Y, this side is Z. The surface area for boxes, it's nice. The surface area is just literally the area of each side added up together. This first side is a rectangle. Its area is X times Z. The back side is also X times Z. The bottom side is X times Y. The top side is X times Y. The right side is z times y. The left side is z times y. So we're getting 2 times x times y plus 2 times x times z plus 2 times y times z. But really just when you draw a box like this, you just find all the areas of all the rectangular sides you have and add them all together. Some of these equations I'm talking about kind of come up more when you're talking about optimization problems, which will be like at the end of the quarter. But it's good to talk about now because we're still useful. And then the volume here is just x times y times z. And then we have a cone. So typically a cone, we draw like this. I always draw my cones in a symmetrical sort of way, meaning like the point of the cone is literally above the circle that's at the bottom. But technically, the equations I'm about to write are true whether or not the cone is slanty one way or the other way. We usually draw them this way, but they can kind of go any which way. So this cone has a radius of r and a height of h. And the volume of the cone is 1/3 pi r squared h. And no one should ever ask you, that's not true. I have seen questions about the surface area of a cone, but they will always give you the equation because it's not an equation anyone should know, in my opinion. I don't know it. I have a vague recollection of kind of what it is, but I definitely would have to look it up. 2 more shapes. Let's talk about the sphere first. No, let's talk about the cylinder first. The reason I like to talk about the cylinder is because I feel like the volume equation for a cylinder kind of goes nicely with the volume equation for a cone. So cylinder also radius of r, height of h. The volume of a cylinder is pi times r squared times h. Or in other words, the area of the base circle times the height. It's kind of interesting. Oops, you can't quite see that at all. In my opinion, it's kind of interesting that the volume of so if you had like a cylinder and a cone that have the same base circle and the same height, the cone is exactly 1/3 the volume of the cylinder, which is kind of cool. And I definitely remember, I think in my chemistry class in high school, like my teacher had a cone and a cylinder that were like containers you could fill up, and you could take the cone container and fill it up 3 times and fit it into the cylinder container, and it exactly fit because the cylinder is exactly 3 times as voluminous as the cone. It's kind of cool. I think it's really cool. And then the surface area equation here is a little bit more of a pain. So what's the area of this bottom circle? Well, it's pi r squared. And the area of the top circle is also pi r squared. So we have 2 circles. And then you have the around part, which I like to imagine that this cylinder is like a roll of paper towels. And I have a paper towel that goes perfectly all the way around. And then I unroll it. And when I unroll my paper towel, what kind of shape do I have? A rectangle. So I unroll my paper towel, and now it looks like this rectangle here, where the height of the rectangle is still h, but the length of the rectangle is all the way around, also known as the circumference of the circle. So that length is 2 times pi times the radius, and the area of the around part of the cylinder is 2 pi r times h. So the surface area of a cylinder is 2 pi r squared plus 2 pi r h. I'm boxing that just to keep it contained from everything else. Of course, I didn't leave myself quite enough room to fit the last shape on there, so we need 1 more page of paper, which is highly disappointing, but oh well. It's only really disappointing to me. I know you all don't care. Bothers me though. Okay, so the last thing is a sphere. Oh, there was one other thing I need to say about triangles. That's fine. So the last thing is sphere. We've got this lovely shape here. Sphere has a radius of r. The volume is 4/3 pi r cubed, and the surface area is 4 pi r squared. It kind of seems a little strange to me, maybe not strange, just interesting, that the surface area, like the actual surface of this shape, is exactly 4 of these circles amount of area. Seems kind of bizarre. Interesting piece of information here, or at least I think it's interesting. The derivative of 4/3 pi r cubed is 4 pi r squared. Also, the derivative of pi r squared is 2 pi r. It's kind of an interesting fact to me that for circular things like a circle or a sphere, if you take the derivative of the thing representing the larger dimension, the derivative of that gives you the next dimension down. I think that's neat. It does not work for other shapes, right? The derivative of x cubed does not give you the surface area, but it works for circles and spheres. And then the last thing I should have mentioned here is right triangles. There are a couple formulas we need to know. So for a right triangle, and then we'll get back to the fun stuff. So for right triangles, there are two things you need to know. One thing is the Pythagorean theorem. So a squared plus b squared equals c squared. Or more generally, you know, the longest side should always be the one that's by itself when you talk about the Pythagorean theorem. Hypotenuse. And then the other thing you want to know is that if you have similar triangles, so here's a couple similar triangles. If you label these, so, and the labeling here can kind of get really out of control. I'm going to label this side, this smaller part here, X, this part here, Y. I've ran out of letters. I know I didn't really run out of letters, but like, I ran out of the letters I like. Let's call this A, this B. Let's call this C, and this D. What I think about when I think about similar triangles is basically sides representing the same length should kind of always be in proportion to each other. So like the smaller side, the smaller base to the smaller height, so x divided by a is equal to the larger base in ratio to the larger height, x plus y divided by b. But there's lots of ratios you could write here. You could do things in the same triangle compared to each other, or you could do, say, like, I don't know, there's so many things you could write here. There's probably like 6 things you could write as far as equations. But basically, when you're talking about similar triangles, just the ratio of any two sides in the smaller triangle is equal to the ratio of any two sides in the larger triangle. So you could say base over height, or you could say height in the larger triangle divided by the hypotenuse in the larger triangle is equal to height in the smaller triangle divided by hypotenuse in the smaller triangle. And what I should really point out, although it's not super duper important, but it's kind of cool, is all these are just trigonometric values, right? When I look at x over a, I'm really thinking about like the cotangent of that angle. It's not really necessary, but it makes it for some people easier to be like, oh yeah, well, of course these have to be equal to each other because cotangent is adjacent over opposite. So it's either x over a or it's this adjacent over that opposite, x plus y over b. Same deal down here. A over c is opposite over hypotenuse. So that's really sine of theta. But is it this opposite of that hypotenuse, or is it this opposite over that hypotenuse? This should be the same. That's why these ratios have to equal each other. Don't worry too much about the similar triangle stuff. We will see when we talk about cones. That's where they really show up. Well, let's go back and yeah, oh yeah, we got so much time. He says now and then 40 minutes. I'm like, not enough time. Okay. So those are all the things you should be aware of. You probably don't need to actually memorize them, but you should make yourself familiar with them so that when you have to use one of them, you're like, oh yeah, I've seen that before. I can remember or try to find where it is. Let's look at something like this. Sorry, I have to think about this one. Yeah, cool. Let's say we have, oh yeah. Yeah, this is a classic problem. So let's say we have a conical coffee filter. Like, you know, like one of the big coffee things, or like coffee, like the old school coffee where they make it in like big drip thing. A conical coffee filter has a radius at the base of 4 inches and a height of 8 inches. And coffee drains into a cylindrical pot, also 4 inches in radius, 8 inches in height. At a rate of, here's right, I'm going to make up a number, sure, of 10 cubic inches per 10 cubic inches per minute seems awfully fast, but it doesn't matter. We're not trying to be reality here. We're just trying to make up a good problem. So we've got volume draining out of this conical filter at a rate of 10 cubic inches per minute, which is probably very fast for coffee. Okay, here's the question. When the height of the liquid in the cone is 5 inches high, or deep, if you want to think about it being deep, how fast is the height or depth, if you prefer that word, of the liquid in the cone changing? It's a lot of words to interpret. Also, I'm not calling it, right, when it's up, before it's filtered, it's not really coffee yet, right? Because it's not magical until after it filters. So that's why I'm calling it liquid, not coffee. Not that it really matters, right? But it's good to be particular. Okay, let's draw ourselves a little picture here. So here's my cone pointing downwards, because it wouldn't make sense if it pointed upwards. And we have some volume in there. And we are dripping out of there like that. So let's label the things in the cone that we know. So first of all, the actual cone itself has a radius of 4 inches and a height of 8 inches. On the other hand, the cone of liquid that is in the cone has a radius that's changing and a height that's changing. So when things are changing in your picture, those things get variable names. So I'm going to call the radius of my cone of water or liquid, not surprisingly, R, and the height of my cone of water, H. I want to point out the height of the cone of water is not 5. It is changing. We're going to do some stuff, and eventually at the end, we're going to be like, okay, now what is happening when the height is 5? But until then, we're just saying the height is something that's changing. We're going to figure out what it is. All right, and we'll deal with the cylinder part of it will come into play in the second half of this question. So now, step 1, what's changing? And this is actually a time where it's very, very important to be specific about what we care about. They told us how the volume was changing. So volume is changing. And we're told that the rate of change of volume is, oh, be quiet. The current volume is 91% of what? I'm really curious now. Okay, anyway, the rate of change of volume is what? How many? You have just enough fingers to show me how many on your fingers. That many, thanks, yeah. Except, is the volume in the cone increasing or decreasing? Definitely decreasing, when we're losing volume. So really, usually when that's the case, you should use a negative number. So we should say that dV/dt is equal to negative 10 cubic inches per minute. And then we're being asked about how the height is changing, or the depth, if you want to call it the depth. We want to know what the rate of change of the height is. Let me ask you all, based on what I just said about the volume changing, are we expecting the rate of change of the height to be positive or negative? Is the height increasing or is the height decreasing? Decreasing, right? Where the height level, definitely we're draining this thing to get all the coffee out. In the cylinder, the height will be increasing, right? The coffee that's going into the cylinder will make the height level rise. But in this situation, it's decreasing. And then I would also mention, although we're not going to write it down, the radius is also changing here, right? The radius of my cone of liquid is changing, but I don't want to think about that too hard because it's not helpful. Here's what I mean by that, really. Let's find the equation. Let's find the equation on the next page. Oh, that's fine. We'll start here. So the equation relating, I would really love it if there was an equation relating just the volume and the height, but there isn't. For a cone, the equation is volume is 1/3 pi times the radius squared times the height. And I really don't want to take the derivative of both sides yet because that radius in there is a problem. So here's what we do in these cone situations. This is where the similar triangles come into play. So let's look at, I'm going to draw this little middle line down here. And I'm going to look at that cone, but I'm really just going to look at that triangle in the cone. Where this side here is 4. This side here is R. This side here is H. And this bigger side here is 8. And now I can write a ratio. I can say that R to H is equal to 4 to 8. I'm trying to write this equation so that I have volume and height as my variables. I don't want radius. To get rid of radius, I'm going to solve for radius here so I can replace it with whatever it's equal to in terms of height there. So 4/8 is 1/2. Multiply both sides by h. I get radius is equal to 1/2 the height. Okay. Now, you can totally do this every time and it works just fine, but there's an easier way to do this. The easier way is to say, look at this big cone. In the big cone, what's the radius? 4 inches. What's the height? What fraction of the height is the radius? Well, if the radius is 4 and the height is 8, the radius is half the height. You're done. That's it. It totally works every time. It's kind of weird, but it really does work. If the radius is half the height in the big cone, any other cone is going to have a similar proportion of radius to height. So whether it's the big cone here or the small cone here, and I know my picture doesn't look perfect, right? My radius doesn't look like it's really half the height, but the radius will always be half the height in this cone because the radius at the top is half of the height at the top. It works. It's nice. I like it. So then back to our equation here, our new equation is now volume equal to 1/3 pi times the radius. We're going to plug in 1/2 the height for the radius squared times h. And before differentiating that, we should really simplify it. So let's simplify. Now we're going to get volume equal to 1/3 times pi times 1/2 squared is 1/4 h squared times h. And then simplifying one more time, 1/3 times 1/4 is 1/12 times pi. H squared times h is h cubed. It's going to be much better to take the derivative of that than not multiply it all out. Cool. We now have our equation relating volume, the thing that we know how it's changing, and height, the thing that we want to know how it's changing. And now, once we got the equation relating the two variables we like, we're going to differentiate both sides. With respect to time. I should mention, not every related rates question has you differentiate with respect to time, but most of them do. Most of the time, we're talking about how something is changing as time goes on, how something else is changing as time goes on. But for a different example, just so I've seen a related rates question where someone says like, you've got like PV equals nRT, like that chemistry formula. And as you like increase your altitude, things change. You ask like how one thing's changing as the other thing changes with respect to your altitude. So it's not just with respect to time. Most of the time, though, it's with respect to time. So that's your usual related rate setup. Here we're going to get the derivative of v is dv dt. The derivative of 1/12 pi times h cubed is going to be 1/12 pi times 3h squared times dh dt. And now we're going to plug in all the things they told us back in the original write-up of the question. So usually at this point, after you differentiate both sides, when you're going to go to plug in, that usually means you have to read the question again to figure out what you're plugging in for what. At least I do, because I never remember. Let's see here. I'm looking back at the question. Well, we know that dv/dt is -10. The 1/12 times 3, we should simplify just to 1/4. Or really, let's write it as pi over 4 instead of 1/4 times pi. They asked us when the height of the liquid in the cone is 5 inches high, so we should be setting height equal to 5 inches. Find the rate of change of the height. I'm not going to write it in, but I'll point out this -10 is really -10 inches cubed per minute. And this 5 is really 5 inches quantity squared. So we're going to get inches cubed per minute divided by inches squared, which will give us inches per minute, which is what we would expect to get if we're asking about how a height of something is changing. Whatever our unit of length is to the first divided by our unit of time. So let's see here. Sure. -10 equals 5 squared is 25. So you get 25 pi over 4 times dh dt. Instead of dividing by 25 pi over 4, let's multiply by the reciprocal. So we get -10 times 4 over 25 pi equal to dh dt. I would probably simplify this because we can totally cancel a 5 here and a 5 here. So I end up with -2 times 4, which is -8 over 5 pi. And that's inches per minute. And our answer, as we expected it to be, is negative, right? We talked about how the rate of change of the height should be a negative number. We got a negative number. It's good that our expectations were met there. What about the rate of change of the height of the volume in the cylinder where the coffee is going into? Good question. Should I pause for a second? For a minute? Because minutes right now, seconds. Right? Any observations, questions, thoughts about this?
How do you know
because of the chain rule. So, but here's an easier answer, I feel like. When we started this off, that's the wrong page, James. Oh, it's right here. When we started this off, we identified, and this is why I think it's important to do this, we identified what's changing. We knew that dv/dt was changing, its rate of change is -10, and we wanted to find dh/dt. And so here's the thing. When you get to the point where you're taking the derivative of both sides, both of those things should show up. If this and this aren't showing up, that's an issue. We need them to show up. And they do show up, right? The derivative of volume is the derivative of volume, and the derivative of some function of time cubed is 3 times your function of time squared times the derivative of your function of time. If it helps, you can alternatively write this as volume as a function of time equals 1/12 pi times h as a function of time cubed. Then when you differentiate both sides, the derivative here, I'm going to use the other notation as v prime of t equals 1/12 times pi times the derivative of some stuff cubed, right? It's more obvious that that's some stuff cubed there is, sorry, and I'm squeezing this in here, 3 times your stuff squared times the derivative of your stuff. But that's exactly right. That's all this, right? There's your v prime of t, dv/dt. There's your h of t is just h, and your h prime of t is your dh/dt. All the same stuff. Yeah. Well, you could, but the derivative of 1/12 pi is 0. So what I'm doing there, although I'm not saying it explicitly, is I'm using the constant multiple rule. When you have a constant, multiplied by a function, the constant just hangs out. We could have used the product rule if we really wanted to, but we shouldn't. The product rule would have been the derivative of this is 0 times h cubed plus this left alone times the derivative of h cubed, which is exactly what we're getting. We're getting this left alone times the derivative of h cubed. Sometimes with these problems, it can feel kind of hard to know when to stop taking derivatives, like how long do we keep applying the chain rule? Essentially, there's not a good way to answer that. It takes practice to kind of be like, okay, I understand what we're doing here. We're stopping because we've gotten to like the base atomic level here where we can't do anything more. Okay, let's go ahead and ask the second question, which is actually easier to answer here. So part B, how fast is the height of the coffee increasing when the coffee is 5 inches high in the cylinder? All right, so we're still pouring coffee out of the cone into the cylinder at the same rate of change of the volume. So for this situation here in our cylinder, where the height is, 8 inches and the radius is 4 inches. And we've got some level of coffee filling up our cylinder. The rate of change of volume, well, now we're adding volume. So the rate of change of volume, instead of being -10, should be +10 cubic inches per minute. And now we're asking about how the height is changing. And just like before, after we have identified the thing that is changing, then we want to know how it's changing, we try and find an equation relating those two variables. So here it's going to be the volume of the cylinder. And I should really say it's the volume of the liquid in the cylinder. So we're going to say this liquid is at the height of H. Yeah, I forgot. Sorry, I forgot. I should have been better about my order here. I should have labeled my picture. And the radius of that cylinder of coffee is R. So the volume of my cylinder of coffee is pi r squared times H. And although I've kind of written this in a way to make it look like we have the same sort of problem as before, where we had two variables, we really only wanted one, we really don't. Because in this cylinder, is the radius changing as the water level goes up? No. In a cylinder, the radius never changes. In a cone, it certainly does, right? As you go higher up, the cone gets wider or whatever way you oriented it. But in the cylinder, you don't. So really, we should have written this as volume equals pi times 4 squared times H. Or really, volume equals 16 pi times H. This is much easier to solve. Differentiate both sides. So when I differentiate volume, I don't just get one, right? I get the derivative of volume, which is dV dt. 16 pi is a constant multiple. So the derivative of 16 pi times H, the 16 pi is going to hang out. And the derivative of H isn't just one, it's dH dt. It's the derivative of H. Again, I know I'm doing this right, or at least I know I'm not. It's not wrong because I'm seeing both of the things I need to see show up. Then we plug in much more easily here, and we get 10 equal to 16 pi times dH dt. So solving for dH dt, we get dH dt equal to 10 over 16 pi, which you really should reduce down to 5 over 8 pi inches per minute. Much easier to answer that question. Just how we got here. Yeah, we got enough time to do these two problems. Cool. I have two more problems in mind that I would like to do. Most of these related rates problems are pretty much the same after you've done the setup. After you've drawn the picture, figure out what's changing, find and been able to write an equation between them. It's really just write the equation, differentiate both sides, solve. I know it seems like they're very kind of different sometimes, but really the process is always the same. So let's look at one of these sliding ladder problems, which I feel like everybody likes to ask the sliding ladder problems. So I hate writing all the words. It's easier to like if I could just draw a picture. So okay. So a ladder lean, let's see. Yeah, sure. A 13-foot ladder. Ladder spelled with a D, not a T, James. Ladder, no. Is leaning against the wall. And begins to slide away from the wall at a rate of 2 feet per second. And I should, yeah. Well, we'll clarify this in a second. How fast is the top of the ladder sliding down the wall when the bottom of the ladder is 5 feet away from the wall? And I'm sorry if the words are hard to read there. I'm trying to write too fast. Let me draw a picture for you. So whenever you see this kind of ladder situation, here's what they really mean. Here's my wall. Here's the ground. And there's some ladder propped up against it like this. And the length of the ladder doesn't change. I mean, technically, right, ladders are extendable sometimes, but like for our ladder, right, the length of the ladder is 13. And they're telling you that the ladder is sliding away from the wall, meaning this point here is moving in that direction at some constant speed. So what we're going to do is we're going to label the distance from there to there. I'm going to call it X. And we're going to say, well, I know that X is X increasing or decreasing? X is definitely increasing. So we know that when we start writing what's changing, our dx dt is the thing they told us. That's our 2 feet per second. Because they told us that the ladder begins to slide away from the wall at a rate of 2 feet per second. If they said it was sliding down the wall at 2 feet per second, then it'd be this value here that was the rate change. Let's call this other length here unoriginally y. And they're asking us, when the ladder is 5 feet away from the wall, how fast is it sliding down the wall? When I first kind of learned this, I tend to thought, well, shouldn't they be sliding like at the same rate? Like, I mean, the whole thing is moving at once, but it's not, because when something, right, if something's moving really fast that way, this part here still can kind of move much slower, or vice versa. So we're trying to find dy dt. Okay, we've identified the things that are changing. We want an equation relating them. When it's a right triangle, you really have two choices. It's either Pythagorean theorem or similar triangles. Those are really the only options you've got. So here, I'm going to relate these two sides by the Pythagorean theorem. X squared plus y squared equals 13 squared. And although you could solve for x or y here, you should not. It's much easier not to. Feels like it just got colder in here. I feel cold all of a sudden. So let's differentiate both sides. What's the derivative of x squared? In fact, you guys differentiate both sides. Do it. I'll remind you, both of these things here should be showing up after you differentiate both sides. See the things I'm pointing to? When you take the derivative of x squared plus y squared equals 13 squared, you should get a dx dt showing up somewhere and a dy dt showing up somewhere. So the next day we meet is the day before your next test. Okay, so I guess we're reviewing on Tuesday. Okay. I don't remember. Did I write you guys a practice first test? Okay, I'll try to come up with something before, like before the end of this week then. Tomorrow, I guess. Yeah. All right. Yeah, I'm gonna write myself a note here. Practice test. Do you guys have 3 midterms or 2? 3? Okay, that I was trying. There was one. I was like, which classes that has 3 midterms? Okay, cool. All right, so let's differentiate both sides here. Derivative of x squared is 2 times x to the first times the derivative of x. The derivative of y squared similarly should be 2 times y to the first times the derivative of y. The derivative of 13 squared is 0. It's a constant. If you really wanted to, you could say it's 2 times 13 to the first times the derivative of 13, but the derivative of 13 is 0. But really, 13 squared is 169, and the derivative of a constant, right? There's no variables there, is just 0. All right, and now let's plug in. Oh, this is one where we have to do a little bit more work. So first and foremost here, you could divide everything by 2 to get rid of those 2's, but I'm not going to, but you could normally. So do I know what x is? Did they tell us in the problem what x is? Yeah, x is 5 feet. Great. So 2 times 5 times, do I know what dx dt is? Yes, I do. It's 2 feet per second. And then plus, do I know what y is? I don't, but I should be able to because the only thing I'm trying to solve for is dy dt. So everything else should be findable. And I can find y by saying, well, if x is 5, then 5 squared plus y squared should equal 13 squared. So if x equals 5, then 5 squared plus y squared equals 13 squared. Y squared equals 169 minus 25, which is 144. And the square root of 144 is 12. I will point out that most of the time when someone gives you a right triangle like this, they almost always, if they try hard, they try to give you nice numbers, like a nice Pythagorean triple, like 3, 4, 5, or 30, 40, 50, or 5, 12, 13, or some multiple of that. So something to be on the lookout for. So y is going to be 12 feet. Yeah, 12 feet times the thing we're trying to find, dy dt, and that's going to equal 0. So let's see. So solving here, I'm going to have 24 times dy dt. I'm including the units because I started with doing it and now I can't help myself. And if I subtract this over to the other side, I have 2 times 5 times 2, which is 20, but it's negative 20 feet squared per second. So if I divide both sides by 24 feet, I end up getting dy dt. That's an S, by the way, not a 5. Sorry, I know. I started writing units and I couldn't stop. So feet squared divided by feet is just feet. So dy dt is going to be negative 20 over 24, which I suppose we could reduce to negative 5/6 feet per second. Does it make sense that the dy dt is negative? Well, let's think about it. If this is sliding down, so I write this goes this way and that way, are the y things getting bigger or smaller? Smaller. So yeah, if something's getting smaller, it makes sense that its derivative is negative. All right, let's squeeze one more problem in. We got 8 minutes. We can make one more problem happen. Plus, it's one of my favorite problems, so we have to do it. So let's say here. Okay. So I'm gonna lie like men do and say I'm 6 feet tall. I'm really 5'10". Really, not like pretend 5'10", like actually 5'10". But there's a whole joke about all that. Anyway, a 6-foot person who we'll call James walks away from a 20-foot street lamp. So we've got and let's just draw the picture. We'll write the meaningful words in here. So, wow, that's horizontal-ish. Here's my 20-foot street lamp, 20-foot high street lamp. And here's our 6-foot tall person. and he's walking away from the street lamp. So a 6 foot tall person walks away from a 20 foot tall street lamp. I'm going to ask this question in the way that I think makes sense, but we'll talk about the other way it often gets asked. How fast is the length of their shadow increasing? Let's just say changing, because let's pretend like we don't know it's getting bigger. When they are 10 feet from the base of the street lamp. Meaning, right, like their feet are 10 feet away from the bottom of this lamp, right? Like we're measuring that 10 feet there. Okay, let's draw the shadow. So like it's going to look like that. And we're asking how long the shadow is cast onto the ground. So we're asking how long is this part right here. So let's call that X. And we're probably going to need this length here. So I'm going to call it, I'm not going to call it 10 because it's not always 10. I'm going to call it Y because it's something that's changing. Technically, these lengths are changing as well, but I don't actually need them here. So it's good to label the things that you can see that you need. And then if you find out you need other stuff later on, you can label that as well. So we are being asked to find, I forgot one very important piece of information. I forgot to say how fast I was walking at. Right? If I don't have one, I didn't give you any rates, and we can't solve a related rates problem if you don't at least know one of the rates that are related to the other rates. So important point or important note. James, who is not really 6 feet tall, is walking at 3 feet per second. Important. Use that piece of information we get written sooner, like right up here. So step one, what's changing? Well, I want to know how X is changing, right? The length of the shadow is what I want to know, or the rate of change in the length of the shadow. And dy dt, how fast the person, right? So dy dt is how fast I'm walking, because it's how fast my position is changing with respect to something that is stationary, which is why we really needed to label this, because that is the kind of given piece of information here. So dy dt is going to be 3 feet per second. And now we need an equation relating the variables of interest. So this is a similar triangle situation. This base in proportion to that height, so x over 6, is equal to this larger base, x plus y, in proportion to this larger height, 20. There are other ways to do this, but this is probably the easiest way. Now, we could take the derivative of both sides right now, but this is an instance where it is actually worthwhile to do some simplification first. Let's cross multiply and say we have 20x equal to 6 times x plus y. And let's actually bring all our x's to one side. 20x minus 6x equals 6y. So 14x equals 6 times y. Much, much nicer. Let's differentiate both sides. Now, check this out. The derivative of 14x is going to be what? Not just 14. 14 times dx dt, right? Because we're differentiating with respect to what variable? Almost always time, right? So when we say I'm differentiating with respect to time, it means the time is the bottom part. We are imagining this x depends on time, right? This length, as time goes on, I'm going to walk that way, and that length is going to change. So x is a function of time, and we're going to differentiate x with respect to time to get dx dt. So the derivative of x is dx dt, and the derivative of 14x is 14 times dx dt. And same deal over here. You get 6 times dy dt. And now I'm going to plug in what I know, which I know that I'm 10 feet away from the lamp, and it doesn't matter. There's nowhere to plug in y equal to 10. So all you really get to do is plug in that dy dt is equal to 3. So I end up getting 14 times dx dt is equal to 6 times 3. And then solving for dx dt, I get 18 divided by 14, which reduces to 9/7 feet per second. Two things are interesting here. Thing one, it doesn't matter how far, assuming like the street lamp can cast like an infinite length light beam and your shadow will work and there's no curvature or whatever. It doesn't matter if I'm 10 feet from the lamp or 100 feet from the lamp. If I'm walking at 3 feet per second, the length of my shadow is always going to be increasing at a rate of 9/7 of a foot per second, regardless if I'm really close or really far away. So I always like to think about this question in terms of how fast is the length of my shadow increasing? Because how far is it from me to the tip of my shadow? That's what I can see. But books or web work or other people will often phrase this in a slightly different way, which is how fast is the tip of my shadow moving? Which means how fast is this point moving in comparison to something that is stationary? The lamp there. Well, it's really easy if we think about it smartly, which is a dumb thing to say, but like it's all I got. If I asked how fast this tip of the shadow is moving, well, the shadow is increasing at 9/7 of a foot per second, and I'm walking at 3 feet per second. I can add those two things together to get how fast the tip of the shadow is moving. Let's actually write it out though. So if I want to say how fast is the tip of the shadow moving, I know. It's almost time. Is it time? Yes, it is. But give me 1 second. Or not. You can leave if you need to. We're just trying to ask how fast is this length increasing? So what's the derivative of y plus x? Well, that's not hard. That's the derivative of y plus the derivative of x. But the derivative of y, we were told was 3 feet per second. And the derivative of x, we just found out was 9/7 of a foot per second. So it literally is as easy as answering the question I like to ask and then adding on how fast the person is walking. So if you ever see a question like this where they say, how fast is the tip of the shadow moving? I would still encourage you all to first answer the question, how fast is the length of the shadow increasing? And then add on how fast the person is walking, because it's just easier.